Welcome back, everyone. We're now in chapter 13 on chemical equilibrium. Equilibrium is what is going to happen in terms of what are you actually going to make? Are you going to make a lot of products? Are you going to not make a lot of products? Are some of your reactants going to work together? Or all your reactants going to work together to make something? Also, it talks about how fast something occurs. So it's not just if a reaction is going to happen, it's if it happens, how fast. So if you have two chemicals, you put it in a test tube, they may instantly react to form a product, or it may take all day, or it may take a million years for it to happen. You have no way just looking at a chemical to know what's going to happen. So there are some ways that you can increase the rate of reaction, that you can tweak it a little bit, and we're going to look at those today. So before we get started, we need to look at a theory of how chemicals actually react with each other. So let's say I have a molecule. In this case, in this picture, I've got a nitrogen molecule, which is an N2. They're bonded together covalently. And I have an oxygen molecule also covalently bonded. These guys are stable the way they are. Nitrogen is stable in the air. It makes up about 70% of the air. It makes about 20% of the air in oxygen. And they're not falling apart readily. But if they are moving around, there is a likelihood that they'll hit each other. And if a nitrogen molecule can hit an oxygen molecule at the right speed, kind of like a car crash, if there's enough energy to actually do damage to the bonds, break those bonds, and then once those bonds are broken, it's just like free magnets that can stick together in certain ways. You could either reconfigure the way they were, so the nitrogen would come back together with the nitrogen, oxygen with the oxygen, or if it has enough energy and the right orientation, if they come together in exactly the right angle, they could split the bonds and then form new bonds. And that's the theory, or that's the kind of overriding theory behind what is actually making new things. How do old things break apart and form new things? And the basic idea is that it has to have enough energy and it has to hit each other at exactly the right angle or the right orientation. So there's way more that you can say about that, but that's the basic theory. So if you realize that there has to be enough energy, then that can give us some guesses of how to tweak in the lab, making something happen faster. So if you were to say, how do you make something have more energy? My first guess is you heat it up, because if you have more energy and more temperature, then you have more energy and it's more likely to happen. In the lab, there's lots of times you're going to have to use a Bunsen burner or a hot plate or something to kind of give it a little bit of push, and then once it has sufficient energy, the reaction will go to completion. Okay, so here's the second page of that theory. If you have, in this case, I've got a nitrogen molecule and a oxygen molecule, and if they go together but there's not sufficient energy, they just bump back apart. Okay. They just kind of bump and touch. It's just like bumper cars. There's not sufficient energy to actually do damage to either car, and so you just bump and then go somewhere else. Also, if they are not configured in the right way, even if they hit with sufficient energy, here's a nitrogen molecule that's oriented sideways and an oxygen sideways, and you can imagine all the millions of random distributions you could have as two gases are striking each other, and they hit with the wrong orientation. They have sufficient energy, maybe, but they don't have the proper orientation. They're not going to break apart and form new bonds. And so they just bounce back. Likewise, if one is sideways and the other is straight up, that's not the configuration. It will simply bounce back. Going back to the first page, if it strikes at the right orientation and with sufficient energy, then if these things are likely to form molecules, then they will. That's how they will happen. So the energy required, if you say sufficient energy, the energy required is called the activation energy, and that's a term that you need to know. The activation energy is the minimum energy needed to break the bonds of the former molecule and form the new bonds of the new. So anything less than the activation energy and the molecules simply bounce back apart and no bond is formed. Okay, if you're talking here, this is you'll see this often, a graph. This is an energy graph. Okay, and so if you have the reactants here on the left, sorry, this is the reactants of the nitrogen and oxygen molecules. They have very low energy. Here you have more energy, there's more energy in the products, but the problem is these are not just going to, if you just gave it this much energy from here to here, that will not actually bring them together. You have to have a sufficient amount of energy required for them to break bonds and form new ones. And this, from where the reactants are to where they actually break and form, is called the activation energy. I mentioned temperature before. That temperature is essentially providing energy into the system. And if I increase the temperature, I will often increase the energy required or the activation energy required to make something happen. So often in the lab, you'll put two chemicals in a test tube and nothing will happen. And then you'll put it over the Bunsen burner. And as you increase the internal energy in that system, inside the test tube, inside the molecules, you will give it the sufficient energy to break the bonds and form new bonds with the other chemicals that are in the tube. Okay, so the reaction rate is how fast that a product is forming, and I guess you could also think of how fast that the reactant is being used up. Think about making peanut butter sandwiches. If you have 2 pieces of bread and a tablespoon of peanut butter, in order to make a sandwich, you have to use the bread. Like if there's 20 pieces of bread, so I have lots and lots, I have no sandwiches, but I have 20 pieces of bread and peanut butter. As I make sandwiches, I'm using up bread. At the end of it, if I have 10 sandwiches, I'll have 0 bread left. So I can think of it either way. I can think of the rate of making sandwiches as either the rate of the sandwiches appearing or the rate of the bread disappearing. And it's exactly the same because the sandwiches are made out of the bread. So either way, it's the speed at which the reactant is used or the speed in which the product forms. And it increases when temperature rises because if you give it more temperature, you give it more energy. As you give it more energy, the chemicals react more hyperly. They bump into each other more often. And the more often that they bump, the more likely that you will have a collision that has sufficient energy and orientation to make a new, to break the bonds of the old molecules and make the new ones. So the reaction rate and concentration. Here's another way we can tweak it. Instead of just raising the temperature of something, I could increase the concentration. For instance, if I have a 7th grade boy with no girlfriend, okay, because there's only 3 girls in his class and they all hate him, well, the chances of him getting a date to the dance is higher if I put him in a school with 100 girls. And then it's actually higher if I put him in a school with 1,000,000 girls. The more girls there are that could tolerate this kid, the higher the chances that this kid's going to go to the dance. And it really, really does work the same way. If I want 2 things to react, by increasing the concentration of one or both of the components, I have more molecules in the test tube. Then there's more of a likelihood that they'll come together. The higher the crowd is, the more likelihood that 2 of them at least will be forced together, and then you'll have 2 of them forced together with sufficient energy and temperature and orientation in order to make a new bond. Here's the last one we'll talk about today, and that's a catalyst. And a catalyst is so used in your body. Your body is full of catalysts. A catalyst is something that's not actually in the balanced equation. It's not part of the reactants. That means it's never going to be used up. But it is helpful in order to make a reaction occur. Sometimes a reaction will never occur without a catalyst, but with a catalyst, it will occur. Okay? The theory behind this is actually really interesting. What a catalyst does is it lowers the activation energy of a mechanism, and the mechanism is how a reaction actually occurs. The actual kind of 3D what's going on, kind of the choreography of exactly how a bond will break and how a new bond will form. And if that catalyst is there, it kind of gives the support necessary for a reaction to happen, kind of like a cast. You put a cast on your leg and your bone grows together the way you want it to, but you don't have the cast for the rest of your life. You just take the cast off and throw it away. It's not a part of you, but it was necessary for your bone to grow well. Kind of works that way. If you can lower the activation energy, then the energy that's already in the test tube may be sufficient to make a new bond. So if I can lower the cost, let's say I want a Ferrari or whatever kind of Lamborghini, something expensive, and I'll never get it. But if you lower it sufficiently, I can afford it. Okay? Once a Lamborghini is $300, I can wait 3 months and probably get one. Okay, that's just the idea. So a catalyst lowers the activation energy of a reaction, and it doesn't do anything to increase the energy, but it may already have the energy necessary if it's cheap enough. Okay? So a catalyst is never used up. It's not part of the balanced equation. It's not one of the reactants. It doesn't become part of the products. It simply is there, and while it's there, it helps the mechanism happen, and then the reactants can react together and form a product. So let's review this. There are three easy ways in the lab to increase the rate of reaction, how fast that something is being produced, product being produced, or the reactant being used up. The first thing that we can do is we can increase the concentration. The higher the concentration of reactants, the more likely they are to slam together at the proper orientation and energy to make a product. The other thing I can do is increase the temperature, and that temperature is related to the energy. If I increase the temperature, I'm increasing the energy, and that energy then will give it sufficient energy to slam together at the right, as long as it's the right angle, it'll work. And the other thing I can do is add a catalyst, and the catalyst lowers the activation energy, is not used up, it's not one of the reactants, but it helps it to happen at a lower energy, which means possibly a lower temperature. That's what a food preservative is, by the way. When you add preservative so that your food doesn't spoil, what you're doing is you're raising the activation energy so that the energy at room temperature isn't sufficient for something to break apart. So if I add a preservative, all the stuff that's going to probably kill us, what it does is it raises the activation energy of a spoilage, and a spoilage is a chemical reaction. So if I can lower it and make it easier for a reaction to happen, then I've increased my rate of reaction. I hope this helps. I will see you in class.